Okay, Hammy here. Today we're going to finish Section 2.1 Nature of Matter, talking about chemical bonding, how atoms and molecules bond together to make bigger compounds. When we talk about chemical compounds, so compounds, there's two or more elements or atoms that are chemically combining. Now, an interesting thing about chemical compounds is the properties can be very different from the original properties. Many of you recognize this picture here. Remember the Zeppelins or the blimps? They had to have a gas that was lighter than air. So they used hydrogen gas, which is much lighter. It's number 1 on the periodic table, really small atom. It's a diatomic molecule, so 2 hydrogens together. And their blimp, was floated very well. Problem was that hydrogen gas is very reactive with oxygen, NO2, diatomic molecule, 2 oxygens together. And what happened is they crashed the Hindenburg into this tower. It caused some sparks, and they ignited the hydrogen and the oxygen in the air into this huge explosion. So you have hydrogen gas, which is very explosive, and then you have oxygen gas. Now think about fire, flames, and oxygen. If any of you have messed and played with jar candles, what happens if I light this candle and I take this lid down here and I put the lid while the candle is still lit? What happens if I screw that lid on the candle? Right, the flame will go out. Flame needs oxygen. So you have this flammable hydrogen gas and oxygen, which fire needs to burn. What happens when you combine them both together? You get a substance called H2O. Yeah, water that we actually use to put out fires. So the properties oftentimes of 2 things combining together become drastically different. And if we balance our formula over here, it actually takes 2 hydrogen molecules, or 4 atoms, combined with 1 oxygen molecule to make 2 water molecules. So the properties become very, very different when they combine together. Now, how do they bond together? Bonds are formed through the interactions of electrons. Remember, in the last video we said electrons are spinning around the nucleus in these outer energy levels. There are 2 main types of bonds we will talk about in Biology 1. The first type is ionic bonding. Ionic is where electrons transfer or jump ship from one atom to another. Now, we said atoms are electrically neutral. They have the same number of positive protons as negative electrons, but that doesn't make them chemically stable. To be chemically stable, we look at 2 things, the octet rule and the valence. The octet rule just says an atom needs to have full outer energy levels of electrons in order to be chemically stable. And because the first level is so small, it only holds 2 electrons to be full. The second level is a little bit bigger. We have 8 electrons, hence the term octet, 8. And the third level in biology will never go past 8 electrons in that level as well. So 2 in the first level, 8 and 8. So whichever level we're at on that atom, with the number as we're filling in electrons, to be stable, the valence just refers to the amount of electrons in that outer energy level, and it needs to be 2, 8, and 8, depending on the size of the atom. So let's take a look at sodium, Na, and we can actually use the periodic table. If we come up here to our periodic table of elements and we find sodium right here, sodium is actually number 11, so that means we have 11 protons, positive protons. We have 11 electrons. Well, when we draw the atom, we'll put 1, 2 electrons in the first level, and then we'll go 3, 4, 5, 6. We fill in these 4 spots first, and we go back and double them up because they don't like to be lonely. They like to have a little buddy. So we say 7, 8, 9, 10. Uh-oh, we're full. We have to go to the next one. Here's electron number 11. All by himself in this outer level. Sodium is very reactive because to be stable, if he gets rid of that electron, it can drop back to a full level and be stable. And nearby happens to be a chlorine atom. So if we go back up to our periodic table, find chlorine, number 17 here, you'll see that we'll need 17 positive protons. You'll need 17 electrons. So we just start filling them in. Here's 1, 2 in the first level. And then we go 3, 4, 5, 6. And we go back and double them up. 7, 8, 9, 10. Go to the outer level. 11, 12, 13, 14, 15, 16, 17. Okay, so 17 protons, 17 electrons. But look, oh, so close to the octet rule. 2, 8, 2 first level's full, 8 the second level's full. Third level only has 7. If it could just get one more electron. So what happens is sodium wants to get rid of an electron. Chlorine would like to gain an electron to be chemically stable. So the electron will jump ship from the sodium and transfer to the chlorine. Now what happens when an atom gains or loses an electron? They're not electrically balanced anymore. They become an ion. So sodium loses a negative electron. So it's going to have a +1 charge. We don't write the 1, it's assumed. Called a cation. Chlorine gains that electron, so it's going to be negative or an anion. And just like in the dating world, opposites attract. A +1 and a -1 will stick together and make this substance that we know as sodium chloride, our table salt. Okay? So that is an ionic bond, gaining, losing electrons, having charges, and then sticking together. The second type of bonding that can occur, and we'll actually talk about quite a bit because most biomolecules use this type of bonding, is covalent. Covalent is sharing electrons. So we'll go back to the valence and the number of electrons in the outer energy level. If we look at oxygen, oxygen is atomic number 8, so it has 8 protons. So it's going to have 8 electrons. 1, 2, and then we go to the next level, 3, 4, 5, 6, and then we start to double them up, 7, 8, 2 lonely electrons. Hydrogen has 1 proton, so it just has 1 electron. So it needs 2 to fill its first level. They said hydrogen and oxygen actually will share one of the oxygen atoms or electrons with one of the hydrogen's electrons. So they each share that spot and thus fill those electron spots or orbitals that you'll learn in chemistry. And in this spot over here, oxygen will share with another hydrogen atom. Okay? This is how we form water. Okay? It's an oxygen sharing electrons with 2 hydrogen atoms. Ammonia actually is nitrogen, which is atomic number 7. So it has 7 protons. So 7 electrons, 2 in the first level. And then we go 3, 4, 5, 6, double them up, 7. Now you notice there's 1, 2, 3 empty spots. So a hydrogen shares an electron in each of these spots, and you have NH3 or ammonia. Carbon was 6 protons. So we have 1, 2 in the first level, 3, 4, 5, 6. It has 4 empty spots, so it can share with a hydrogen in each one of those spots. Okay, these are all what we call single bonds. They're sharing one pair of electrons. It's a single bond. Sometimes atoms can share 2 pairs or 2 from each atom. Okay, carbon had 2 in the first level, had 4 empty spots. Oxygen has 2 empty spots, so one oxygen atom will share 2 of its electrons with 2 of the carbons here. We'll share 2 with this oxygen. So this is what we call a double bond. Carbon is double bonded to each oxygen atom. We can actually get a triple bond as well. If we look at at N2, which is 80% of the air, the atmosphere around us, is actually nitrogen sharing 3 electrons in its outer level with each other, okay, in a triple bond. There is no such thing as a quadruple bond because that bond would be way on the other side of the atom, and if due to physics there is no way that bond can bend all the way around the atom. So there is no way for a quadruple bond, but we can have single bonds, double bonds, and triple bonds when we talk about covalent or sharing electrons. Okay, so when we look at atoms after they combine, we often write them out in chemical formulas. Chemical formulas will tell us what is in that compound, what atoms, and how many of each. So we use atomic symbols and numbers for each of the atoms. So if we look at our compound here, we've got aluminum sulfate. Let's say we have 3 of them. This is what we call a coefficient. Big number. Tell us we have 3 aluminum sulfates. So if we list our atoms, we have aluminum, S is sulfur, O is oxygen. How many of each in 3 aluminum sulfates? Well, 3 times 2 would be 6 aluminums total. Now, how many sulfurs do we have? Well, we take 3 outside the parentheses here. 3, this is like there's a 1 there. We don't put it, it's assumed. 3 times 1 is 3 sulfates times the 3 coefficient over here gives us 9 sulfurs. Oxygen, there are 4 here, so 4 times 3 is 12, times 3 is 36. Okay, so this is the total number of atoms in 3 aluminum sulfates. Okay, the chemical formula tells us what exactly and what proportions are the different atoms in the molecule. The other way that compounds can be represented are with structural formulas. This shows us the structure or the arrangement of the atoms, how they're linked, how they're bonded together. So if we go down, here's our aluminum sulfate, okay, our Al2SO4 3. Okay, so here's a molecule we just looked at on the previous slide. This shows us using chemical symbols aluminum. So there's our 2 aluminums. We had 3 sulfurs just in one molecule here, and we should have 12 oxygens. You can count them. So it's showing us where the atoms and which atom is linked to which atom. Okay, each one of these lines represents a bond or a pair of shared electrons. Between the sulfur and the oxygen, there are 2 lines. That is a double bond. And if you look over here is carbon dioxide, which we said previously. Carbon is covalently bonded to 2 oxygen molecules. Okay, they're sharing 2 pairs of electrons. Here's nitrogen, N2, which is like 80% of the air around us. Okay, it's just a triple bond, 2 nitrogen, what we call a diatomic molecule, 2 nitrogens triple bonded. Oxygen, okay, which is about 20%, well, 19% of the air around us, 19%. It's just O2. Here's how we would draw the structural formula of water. Okay, oxygen sharing an electron with 1 hydrogen, sharing electrons with another hydrogen. Methane, which we showed previously, CH4. Just showing the arrangement of the atoms and how they're all put together in the molecule. The last thing that this section covers, just briefly, is what we call van der Waals. Van der Waals bonds are very weak bonds, but they do some amazing things. And I think your book brings this up because in the animal kingdom, in the natural world, we see some very amazing things, like the geckos. If you've ever seen geckos, you can search YouTube and you can see geckos climbing up the glass walls of an aquarium or up the wall. How do they do this with? Well, they have very special feet. On their feet, if you zoom in, you see these little strands or lamellae. And if you zoom in on the lamellae even closer here, you see they have setae. And if you zoom in even further on those setae, we see it's even further divided down in these little flat not suction cup things, but just flat pads, 1 micrometer, teeny tiny. You can't see that looking at this big gecko hand, but there are these little tiny seedi provide a real weak attraction between the foot, the tissues, the cells in its foot, and also the glass wall or case that it's climbing on. And this allows the gecko to actually stick to the wall and can climb straight up a wall. So I hope you have a better understanding of how atoms and elements can kind of combine together. We're going to use this later in the chapter to start building big, what we call biomolecules. Okay, those lipids, proteins, nucleic acids, and carbohydrates that make us up who we are. So I hope you hope this helped. Hope this helped you understand atoms and molecules and bonding better. Thanks.